our discussion, our introduction to SynthDef has potentially opened a sort of can of worms, because indeed one thing is to understand the syntax at the base of the connection of various UGENs, while another thing is to understand why to connect certain UGENs to other UGENs. And of course this is a sort of much wider topic, because it involves in a general way electronic music theory and computer music theory, two domains that overlaps largely but not entirely. So of course we have no time to discuss this such a wide topic, and what we will try to do in this video is to introduce probably the oldest technique in sound synthesis. First of all, because it is interesting in itself and it is a synthesis technique, so you don't need anything else to generate sound. And secondly, because it will allow us to discuss some other aspects of about the way in which SuperCollider handles, let's say, the server handles the process of creating synths. So, what is additive synthesis? Well, it all starts with a very famous theorem that probably you know, the Fourier theorem. This theorem states that if we have a periodic waveform, complex periodic waveform, that is a complex waveform that repeats itself, well, it is theoretically possible to decompose this complex waveform into a sum of sinusoidal components, frequencies, well, let's say sinusoidal signals that have some specific properties, so each one with its own amplitude and phase, and those sinusoidal components are all related by the fact that they are all integer multiples of the fundamental frequency of the original complex waveform. So the idea is that we can create a sort of analyzer that is something that takes as an input a complex waveform and outputs a set of sinusoidal components, each one with amplitude and phase, and related by this harmonic ratio, meaning that we have a fundamental frequency, the lowest one, and for a sinusoid, and the other sinusoids, they have frequencies that are integer multiples of this fundamental frequency. Given that, it is possible to reverse the same logic and to move from analysis to synthesis. So the idea is simply, given that relation between complex waveform and sinusoidal signal, we can take sinusoidal signals. They are easy to generate. We know how to generate sinusoidal signals. We can take sinusoidal signals with their specific features in terms of amplitude and phase. We will discuss about phase, and we can sum all these components and create a complex waveform. So we reverse the logic, going from analysis to synthesis. It is additive synthesis because we're adding sinusoids, and just to be clear, to add a signal in the digital domain simply means that for each instant, at each sample time, we take all the values of all the components and we simply make a sum. If a component is 0.2 and the other is 0.7, we simply do 0.2 plus 0.7, 0.9. That's pretty easy. So how do we create a complex periodic waveforms? Well, first of all, complex periodic waveforms are interesting because typically they are the kind of output of music instruments having pitch. So a pitched instrument in some way it generates a complex waveform, steady waveform having a certain basic frequency. So if you're playing an A on a clarinet, you will get a complex waveform with a fundamental frequency of that A. Let's suppose 440. So that's why, of course, additive synthesis is interesting, because it is targeted at creating periodic sounds, periodic signals, that is pitched sounds mostly. So it has a specific application domain. So let's suppose we have this idea: create a complex sound by means of adding sinusoids. How can we do this in SuperCollider? Well, we can start with the SynDef, and we call it add, and add in the sense that additive, let's call it additive. And suppose we have a frequency which is 110. We could say that we have var f, which is sinus r 110, and we could consider that we have three components like f. Well, let's call this f0, f1, f2, and let's say f3. So we have the fundamental frequency, and then we will have something like this, something like this, and something like this. So the idea is that we have 4 sinusoidal components. All are multiples of a fundamental frequency that we have hard-coded here. Now, if we have all these components, what should we do? Well, we can simply do something like var add, and we say add is f.0 1. Okay, and so we output the sum. Right, so let's consider this. We will have some issues here that we have to solve. So we can make a synth like our add. And no, it's called additive. Now if we scope this, well, there are some issues. The first one is that first of all, we're summing all these normalized signals, and the point is that they will all reach their maximum, absolute maximum, +1 or -1. So if we just sum them, it is highly probable that we will go over the maximum range. So this means that this add signal will have an amplitude, an absolute amplitude greater than 1, be it plus or -1. So we have to scale the amplitude. What can we do? Well, we could scale all those amplitude, but one of the possibility is to scale this. Scales, meaning that we multiply times what? Well, we could observe that to be cautious, we can divide by 4, that means multiply by 0.25. So And we have our stethoscope, and this is entirely included into our normalized range. This is very important because in order to avoid any issues with distortion, you have to keep your audio signals, final audio signals, in the plus or minus 1 and minus 1 range. This is the audio range. What happens if you go over this range for audio signals? Well, it happens that this range is the maximum range that we are able to represent on our computer, and so if there is something greater than 1, like 1.2, then it will be cut to 1. So it will be clipped. Technically it's called clipping. So it will be clipped to 1. So imagine you have a sinusoid like this. If it goes over the +1 barrier, then all those samples greater than this barrier will be clipped to 1. Now, if you look at what happens, you will see that you have no more a sinusoid, because reaching the top, all the values over the top will be will be made equal to 1, so you get a different waveform. It will start squaring its shape, and this means you're changing the waveform, and if you change the waveform, you change the spectrum, and you change, of course, the way it will sound. So you should always avoid clipping in the final result. Of course, this does not apply at all to control signals. Control signals are used to control parameters. So the point is that their range depends on what on the parameter intended range. So if we look at this SINDEF, we see that it is pretty boring, in the sense that we are substantially copying and pasting line like this, and we have only 4 components, while typically in complex spectra of acoustic sound they have many more components. So of course we can keep on copying and pasting, but this will be quite boring, and surely this is something that in some sense clashes with our approaches, which is a procedural one. Can we do something better? Well, the first thing is that of course we use an argument. And maybe also we want to control where we place on which bus we place our sound. So now we can have something like this, and we do something like well, let's see what's going on here. Something like we're adding 3 components. Again, we have a clipping issues here because we're still adding on the final bus. This means that while creating these various synths, there were 3 synths, we were writing all those signals into the same bus. So at the end, the bus can contain values between -1 and +1, and we'll still having clipping issues. So what can we do? Well, we can do something like this. Add another argument. New line because of this. So something like 0.2 and we do something like this. So these new arguments acts like final volume on our synth. So still having, I don't get exactly. I'm very sorry. This should not be here. Of course, this is the bus, so you cannot multiply the bus number. It's curious that it works. It should be here. And this is what we see. Okay, so fine, we have an harmonic generator. Well, it's more complex than our classic sinusoid. It starts having a sort of organ-like tone with these 4 components. Now, as you might remember, I say that for Fourier, we need to specify the phase and amplitude of each component. Of course, we haven't yet, and this means that they are having all the same amplitude and they're having all the same phase. Now, let's look at this. If we're looking at our sinusoid, we can see it as a sort of spike, and a spike, and then a sort of lower block. Maybe we can try to plot this directly. No, that doesn't work. Maybe because we have this. Okay, some issues here. Let's see. Okay, this becomes very clear here. We have a spike here, and then a lower block, and then a spike, negative spike. Now, this is periodic, so this means that, again, it will start with a spike and a lower amplitude block. Is this normal? Yes, of course. And why do we have this specific behavior? Well, if all our components, they all starts with phase 0, it means that they all start by making their sinusoids. So the point is that in the beginning phase, all our components have an increasing positive value. So they are all targeting 1, let's say, their amplitude. Now, of course, they're targeting this peak at various rates because they have different frequencies. They have multiple frequencies. So at a certain point, they start going out of phase. But initially, they are all raising. So as you can see here, they are raising here, and they provide this peak. Now, at the end of the cycle, they keep on getting again on phase, because here they will be on phase again. And this means that they will repeat this behavior. So the point is that here we have a large peak, and here we have a much lower peak. An interesting aspect of periodic sound is that our here is not very much interested in phase. This means that we can change the phase and substantially it sounds the same. So a possible technique is that we create a random phase like this. Let's see if this works. This is one of the possible approaches. Now, if you look at the plotting of the function, well, it's getting different. So let's try another one. So we're having a random phase, meaning we start in the middle, in one of the possible moments, let's say, of the signal, and this applies to all our signals. So their sum substantially is well, is never it does not replicate that specific peak behavior. So let's consider this block as a good one. let's take this as an interesting block, and let's copy this here. Now let's see if this work. We're still having, this is a bit, let's try another one. We're still having this let's look at this. Okay, let's use this. Probably it's better we use a Eugen rather than generating because we're using it while generating a scene. Let's try this. Maybe. Okay. I'm sorry, I'm making some mistakes today. Rand. Now, Rand is a Eugen. Rand is a Eugen, which does not generate a signal. It generates a single value. And okay, let's try this again. I was making a mistake because I was having I was not looking at the post window, and this is interesting because there were some issues and I was not able to spot them. So that looks better. Looks better. Okay, that's fine. So actually, the point is that I was using 2p rand, meaning go from 0 to 2p, but it is an interesting issue because that means that once the SYNDEF was created, that value was set and remained fixed for all the scenes because it was built in inside the SYNDEF. Now what happened here is that I'm using rand. Rand here is a Eugen that does not generate a signal, but every time, as you can see from the help file, every time the SYNDEF starts playing, well, actually means the synth is created. When the synth is created, a new random value between 0 and 2p, so it is expressed in radians, is generated. So this means that every time we create a synth, we get these 4 random values, and that works. As you can see. Okay, so fine, we have solved this issue. Well, we made some fuzz, but at least we understand a possible issue of complexity. Now, still, this is better, but still we do not like this block. Can we do something better? Well, of course, it's pretty clear that we have a relation between these components because they are all based on FR, the parameters of the frequency, and they are multiple. So can we express this in a procedural way? Luckily, yes. So bear in mind that the server can only understand relation between Eugens. But the point is that while creating the SYNDEF, and we're writing it on the language, on the interpreter side, we can express those relations in a more compact and procedural ways. So, as an example, when we see this, we can say, but why can't we have something like, it could be, well, this could be a series, like we want to have frequency like array series starting from, well, these are 4, and we start from FR, and the step should be FR. So we have, well, we do not know what is FR right now outside the SYNDEF, but we can say that we have an environment variable like FR, this one, and thus That's easy. So can we use this in well, useful way? Well, actually, we could also think about something like this is interesting because we're expressing relations between all those values, and by the way, it could be done in this way if we want many. So let's suppose we have var arms like this. This time we're sticking to this value. Now, how do we feed these? Well, actually, there is a specific technique which is very interesting, which is the following, and it is called multi-channel expansion. I'll give you an example. So you can have something like var seg Now, this is not exactly what we want, because there's still an issue, but it can be interesting. So what happens here? What happens here is that if you look at the code, you see that we are creating an array of values, and we're feeding this array to Sinoscar. Now, what happens when we give a huge greater than a single value, as expected, an array of values? Well, this is not so obvious. It should be encoded in some way. And in fact, there is a convention and a mechanism that is called multi-channel expansion that I might show you here. It's not add, it's sig. Now, do we need yeah, well, actually it should be, this should be made more interesting, because 0 dot 1 to 5 means 1 8, and it is related to this, but we are not expressing this relation in any way. So maybe var arm num, so the number of harmonic, this is hard coded, but we can say that var dim, and now once we have this, we can use this number here, and we can use this number here as reciprocal. What does this reciprocal mean? Well, you can see that if you have one reciprocal, it's 1, but if you have 2, it's 1 divided by 2, and if we have 4, it's divided by 4, so actually it's 1 divided by that number on which we call reciprocal. So if we listen to this, but that sounds dull, and in fact where is my scope? It looks like it doesn't work. Well, there is only one sinusoid, but this is wrong actually. So I'm doing something bad. Ah, yes. Yes, it's a pity you are not with me physically, because you will have corrected me. So this should be arms. So now we are passing an array here, and in fact, before we were passing just fr, which is 100. So correctly we had one single component. Now this should be, well, these are typical issues when you start modifying things, so you're not keeping track of all. Okay, so this should work. Yes, it is. And you might say, okay, that's a little bit more interesting, but still less than what we were hearing before. So the fact is that if you see now, we are generating 8, you can count them, 8 signals. The point is that those signals are sent to various buses. So this is 0 left in our stereo setup, this is 1 right, and this is what? Well, if we are in stereo, these are the main, the two, let's say, public buses, and these are internal buses. So what is this mechanism doing? Well, what happens here is that we have multi-channel expansions. It means that every time you feed a Eugen with an array, during compilation, what happens is that the interpreter is seeing this array and start branching. So it starts creating various signals, and when you pass here sig, now sig is an array because it is an array of sinusoid, because we have provided an array here, and so we are generating an array of sinusoidal signal as output by sinusc. And so as we're passing an array here, again here we have multi-channel expansion. This means that they will be distributed from this number, which is 0 by default in our case, to 0, 1, 2, 3, 4, 5, 6, and 7 in our case. So this idea of multi-channel expansion is very interesting from different perspectives. The first is that we are able to generate arrays of signals in one shot. And the second is a direct application of this concerns exactly multi-channel setup. That is the idea of delivering audio through various channels. Until now we were in mono, working substantially with 0 or 1. Now we see that we can generate array of signals to be immediately distributed over various setups. So suppose you have 8 channels, maybe an installation, maybe an electroacoustic piece. Well, it's easy to generate in one shot all these channels and just send the array here, because this is an array, because this is an array. So providing an array to a Eugen, we generate an array of Eugen, and giving an array of Eugen to out, we have an array of out. So it's an easy way to control multi-channel setups. So you might say that this is cool, because this is very cool. The point is that we are not getting a complex signals. Rather, we are getting not a complex signal made up of 8 components, but we are creating 8 signals. And the point is that originally we were summing all these signals up. And in that way, we were obtaining a complex periodic signal. So yes, this is interesting, but how can we have a single signal? Well, actually we have an interesting Eugen, which is called mix. Mix, like rand, does not take R, but it takes new. So as it takes new, we don't have to specify it. And mix is a mixer. So you pass an array and you get a mono output. So what happened with mix is that you're mixing everything going to mix into an array. So the array of signals are all summed up so that we have final for each samples in a certain, how can I say, position. We will have in output the sum of these values. So we're summing up all the signals in the array we are providing. And which is our array? Well, this one. This was an array. So we call this variable mix, not such a fantasy. And then we provide mix in the output. Let's see if we made some mistakes or not. Well, this sounds mono, Again, we're having some spikes. And why are we having some spike? Hadn't we solved this issue? Well, first of all, notice that the point is that we are generating a series of harmonic components in one shot by means of creating an array and exploiting multi-channel expansion. That's really cool. Now I'm mixing everything down, or mixing up, and passing this mono signal, something going out from mix, multiplying it by our scalar and passing it to out, and we have, of course, it's mono, so it will be written only in this bus. We are having again this phase issue, and this is interesting. Why? Because if you see here, this is an array, so as this is an array, we are forking, so we're branching and creating various synods. How many? Well, 8. Each one of them having one of the frequency of our arms array, and which phase? Well, the phase is just one, because it's this number which is triggered once every time a new synth is created. So this number is one number, and it's all the same value for all the components. So even if we do not start with 0, they are all starting at the same moment. So they will start offset, with an offset, but all in phase with each other. So the point is that we have to change this. Can we do this in a more interesting way? Well, we could do something like this, but there is something better, something like and we create an array fill of arm num, filled with what? With rand 0 to p. Now at this point here we should pass ph. So we're creating two arrays and passing to Synosk an array here and an array here. What happened here is that we're picking the relative element from each array. So first from one associated with the first from one from the second, and we get the first sinusoid. Second from arms, second from ph, and we get the second sinusoid. Let's see if I am right, because I can be wrong, of course. Let's see our scope. It looks much better. Let's kill everything and start again from scratch. Well, this is right. Cool. Can we do this in a more elegant way? I think so. Because here we created arrays, a couple of arrays, but maybe we can create a single array. Now, please remember that there are no arrays on your server. This is a definition, a linguistic definition, and the interpreter, while compiling, will create all these complex network of UGent with their relative values. So the point is that this is a procedural way to specify a graph which will be expanded on the server. So the server does not understand array, nothing about that, but it's an interesting way to procedurally specify the way in which we create an instrument. So rather than saying that an instrument is made up of all these parts, we are saying that we create an instrument by means of a certain procedure. It's just like while providing instruction for mounting a key to say repeat these n time. That's the point. So we can have something like var_sig array fill arm num for 8 block. We are trying to create on the fly Synosk are trying to create on the fly all the signals. Now here we need this specific relation. So we know that fill with array is a constructor method, and you can access the counter. So we call this I, and we say that we need I multiplied from so that is times fr, but I originally is the counter and will be 0, and so we need to add an offset like this. There is something I probably never said, and it is important that I say this. The thing is the following one. If you might get in trouble with something like this. Plus 3, 4, 7. Now, what's the result? What's the result of this? Well, 7 times 3, better, times 7, it's 21. So this should be something like 21 plus 5, 26. And here we get 56. Why? Well, actually, it's pretty easy to understand. You get this, 5 plus 3, it's 8. 8 times 7, it's 56. So what's happening here? Well, what is happening is that, of course, there is no operator precedence, operator priority, as you want to call it. So this means that, differently from what we are used to from school, we will not do first multiplication and division and then some plus or minus, but they will be executed in order. So this will put into trouble sometimes, it will happen. But if you want to be sure, don't want to take this into account, you just use parentheses like this and this. So in this case, this means priority to this and then to this operation. So back to where we have started. Right, so we are creating what? Well, we are creating an array, this time, containing what? Containing signals. So the output of sinus R. And so we have to create the right signals. So this is the correct frequency. We start from FR, then we add FR multiplied by the counter, which starts from 0. So the first block will be 0. And then we will have FR as the fundamental frequency, and then we will add harmonics. Yes, do we want to check this? So if this is 200, if this is 100, and this is 1, we have 100 plus 100, and if it is 2, we have 200 plus 1. Okay, so it's an offset. Now, the question of the phase. We can use this. What's the difference between what happened before? Well, the point is that we are creating... Can we do this? I'm checking. We are creating a random number which is triggered every time it is called. So the point is that this is a different... There are 8 Eugens, and this means that there are 8 Eugens like this. Each of these will get a random number when the synth is created. So this should work as expected. Now at this point, if we have sig in this way, we can always multiply for our cautionary scalar. And let's see what's going on. Sounds right. Okay, here we are. Let's add another one on stereo in this case. Let's see the 2 signals. So we had another signal as to right, and another one. Okay, that's a bit how can I say, a bit obnoxious, but you see that we are creating blocks of 8. Now, block of 8 sinusoids to create a complex waveform, a bit, how can I say, noise-like sound, but that's interesting, and we can use this instrument and we can make it more complex. Now we cannot change this number in real time, because the point is that this number is used to create on the server, in the definition of the instrument, a network of fusions, and this network cannot be modified in real time. So the point is that when you create a SYNDEF, that's the way it is on the server. You can change the SYNDEF by sending again a SYNDEF, but you cannot modify that SYNDEF. It's just like modifying a project while you're doing it. It doesn't work. So we cannot pass this as an argument, but sure, we can create a new, more complex. You see, we're getting this kind of nosy sound, a bit like how can I say, a sort of bassoon or other kind of reed instrument. And can we use this instrument? Well, of course, let's do something pretty easy. Now, I'll tell you a secret. This create and execute, creates and execute a routine. So, rather than writing routine, new routine, play, we have a function, the function that should be inside the routine, so the core of the routine, and we call on this function fork. It's just like when we were doing play. By saying that it is play, we assume that it is a Eugen graph function, so a SYNDEF is created and a SYNTES instantiated. Now if we write fork, it's just like assuming that this is the description of the function to be put inside the routine, so the description of the behavior, and a routine is automatically created for you. This is quite useful, like function play. So we can do something like this, and I'll tell you another secret. You can skip this and you can do this directly. This is not correct because you're respecting over theoretically correct, because you're respecting parentheses here. This is parentheses because this is a method, am I right? But you can skip this. So you can write directly in this way and omit some parentheses, because you're getting a little bit crazy after all those parentheses while working. So there's some shortcuts that can be useful. So infinite time do. Infinite time do what? Well, we can. Well, let's create this sort of. Well, we can change. We can change. We create a synth here. X will be our synth in the shape of an additive one, and we are not passing any parameters, and then we do something like having f such as an array of pitches. I'm sorry, I'm always working with pitches because it is an interesting way of understanding the use of data to control, to convert them in the right form. So 0, 2, 5, 7, 11, and then we introspect something here, right? Then let's do something like this. Then infinite time, we say that we have x set, what? Well, we're using this, and so we want to have f. Let's use our classic style. So we like here. So we can say that we want to access to the I element, but we need to use a modulo f size. And we have to add an offset. This offset can be chosen between, let's say, 48 and 72. No, 48, 60, 72. Choose, and all these should be converted into from MIDI to CPS. Let's go on the new line. So out 0 1 choose. So we're choosing the out randomly. So what should happen then, we have to check, is that we're going through this pitch sequence, add one of these 3 octave randomly, and convert this in hertz, then selecting a random out between on a stereo configuration. Okay, that's interesting. What are we to do? This. Fine. We don't have anything working, so we have to boot the interpreter. This is a good mistake, because it's a mistake, I told you. Server. Okay, so we did the classic. We omitted the wait. So we were executing very fast all this, and of course everything crashed. So now we have to start again. I have restarted the interpreter, and now we'll have to restart the server. Now I will have probably to do also something like this here in my configuration. Yes, because SuperCollider server was dead. So we're making a lot of mistakes today, but that may be interesting. So now we have to add this SYNDEF, because as we shut down the server, the SYNDEF is gone. Let's check if this works. Fine. So now maybe this should work. Am I right? Yes. Okay. So this is an instrument we can control live. As an example, we can add add a control for frequency, like with a knob. And we can also try to make it a little bit more complicated. As an example, the point here is that we say that for the Fourier theorem, each component should have its own phase and amplitude. We saw that the phase is substantially irrelevant in case of stationary sounds like this, really periodic. So our ear is not really interested into that. So we can use random values. The point is that amplitude is very important, because typically in acoustic situation, what happens is that there is a spectral envelope. It means that the various components, they can have various amplitudes, and many times, even if not only, this envelope for like a flute or a clarinet or a violin, you have something like this. It means that the fundamental frequency is the stronger one, greater amplitude, not always, but most of the times, and then you have a general decrease in amplitude for the next component. So the first harmonic is a bit lower in amplitude than the fundamental, the third is lower than the second, and so on. This results substantially in a typically more acoustic-like sound. And interestingly enough, this noise quality of our sound is also related to the fact that all our components, they have the same amplitude and is the maximum amplitude. So can we work on that? Well, we can have something like a third argument, fourth argument, like let's call this decay. It's a spectral decay. And how do we use this decay? Well, let's suppose we want to have a decay of 3 dB, because we have to work with dB, otherwise we cannot control this, in our amplitude. So the point could be that here we have the phase while creating our sinus, and our mul argument, the next one, as you can see, is fixed to 1. So the point is that we need to have 3 neg. Why? Because 3 neg means minus 3. If you want to check, can check it like this, 3 neg, and you get minus 3. So you have minus 3 that should be multiplied by our counter. This means that the first the fundamental frequency, this is 0, so no amplitude decay. So the second will get a 3 dB decay, the second a 6 dB decay, and so on. Let's see. So if we have 0 here, this means that this will always be 0. The point is that here we are not working with dB, and we have to work on with dB. So let's, if you want to be more clear, particularly with yourself while studying, you can do something like this and use keywords. So this should be mole, and this must be converted into linear amplitude because we are thinking in dB. So let's suppose that we have 0. So this should not be, this should be our decay parameters. If we set this to 0, this will always be 0, and so we will have 0 dB amp. What is going on with 0 dB amp? Remember that 0 is the maximum, and we get 1. And if we have -3, it will be scaled by 0.7, and we have -6, it will be scaled by 0.5. So in fact, when you are at half the maximum amplitude, you're losing 6 dB. So let's take a look at this. There's a mistake. Where is it? Where arm Here it is. We have another mistake. That's normal. Var mix. What's the point? Let's look at this. Parse error. So we missed something here. Opening brackets. Okay. So we are losing. We lost a bracket. Fine, you see that you have auto-completion of parentheses. Parentheses matching is called. It can be very useful, so let's check our parentheses. Fine. It's a typical mistake, you're losing anywhere a parenthesis. So let's have this and call this x. X set decay. You see that is more noisy, it's richer in higher components. So do we want to see this? Yes, but this time it's important that we see what happens in with our frequency analyzer here. So let's do this. These are all our components. Let's see them linearly, and let's use a 3 dB decay. You see we have a 3 dB decay for the components, and we can have a 6 dB decay. Now at this point, let's do something a bit nasty, like 24 components. So we can do something like this at this point. This is interesting to check in real time. So we do a block with a window and like width can be something like 250 and 8 no, we do width 500, 8 250, front, and we made a K, which is well, we can do something like SL new object slider v rect it should be 0, 0, and then it could be large 500, and 8 could be 100, and then we can have SL2, and it's a slider, and like this, and we can copy and paste. So we're making a window with two sliders. What is a slider? It's like a knob, so the only difference is that it is linear. We have to start, let's say 250. Let's see graphically what's going on here. One is wrong, the other is right. Where is the other one? Okay, no. What are we missing here? 0, 0 is the position, this is the width, and this is the 8. This is the width, and this is the 8. Yeah, but this is wrong. Okay, so we should have two sliders. This is not beautiful to see, but it works. Now this is like exactly like a knob, 0 and 1, and so we use actions, and so we say that our action for SL action is SL dot action is, the action is a function, and we know we need the slider itself, and the first action will control what? It will control the fundamental frequency. So if this is the fundamental frequency, we need to do X, provided it is working, X set FR with what? With something like me value, the value of the slider, that must be linearly mapped, and let's do this in this way. 0, 1 is the domain of the slider, and we want to go from, let's do 4872 milli CPS. So we're thinking linear. This is linear in terms of pitch, even if it will be continuous. Fine. On the other side, we need another action for SL2, and we want to control this decay. So X set decay. Now, you know that this is always 0, 1, and this is the amount of decay. So 0 is the base. Well, it can go from 0 up to what? I think we can do something like 12 should be enough. So let's create the synth, and let's add our actions. So where's the action? Where's the maybe I've closed it. Yes, so we need to make it this. Yes. So let's see what's going on here. Fine. Maybe we can have a little bit like X set, it was called amp. Let's give 6 dB amp. Maybe 3. Okay, now let's see what happened here. We're controlling this in real time, but there is something wrong here. Because this 0 is mapped to there is a mistake in here. Let's close this and let's inspect what happens. Decay me value len. Oh yes. Oh yeah, copy and paste is always an issue. Let's give some. So we're controlling both parameters. The mistake we were doing is that we left this MIDI CPS that was doing some strange things on our values here. And of course we can use our SyncDef here and modify in order to use something like we were setting a frequency. Now we can set also decay, and we can use decay as E, which starts from 0, which is fine. Modulo 8. So let's see if yes, no, today is not a bad day, a good day for typing. You see that the sound is richer and poorer because the decay is modulated, is modified by the counter progressively. Well, now, of course, just to the idea is to add control, a very possibility of control, and of course, this SyncDef creates an instrument that is something which stands there, and we can modify it by tuning knobs. As an example, we can control, in this case, amplitude, out, decay, frequency, whatever. Now, this multi-channel expansion thing is very interesting because it is originally it was thought for multi-channel, but actually, so for sound spatialization, but actually it can be used as a syntax construct to create arrays of signals that can be mixed down, and so you can create your own SyncDef in a really procedural way. But the point is that originally multi-channel expansion was thought, as the name says, for sound spatialization. Now actually we're simply using out here to define where we wanna place our sound. Now bear in mind that you can have many out on your SyncDef. So if you want to, you can have something like this, like out plus 1 and out plus 2. This means that the same signal will be written on 0, because this is our default value, 1 and 2. So you can have many output as you want. By the way, as usual, take a look at your code as we're copying and pasting. Here we're doing 3 multiplication, 3 times the same operation. So at this point, it's better to do something like this. And here we're just forwarding these signals, and we do 1 multiplication rather than 3. So there's always there is always this open topic. If you want, try to look at the code and see if you can avoid wasting computation. Computation on the server can be expensive because it deals with generating audio signals. Now, of course, you can have your you can write in with different outs on different buses, but let's suppose you want to do something like having the sound only on your left, or maybe only on your right, or maybe in the middle. What does it mean in the middle? Well, typically what happens is that now let's consider we have a sound source here. Now the point is that it will reach substantially here, and the point is that I will locate the sound from this part, and if this is on the other part, it will reach my here. So big sound pressure, that is big amplitude of the signal here, theoretically 0 on the other side, and I will locate on this part the sound source. So if I have a sound source here, the point is that the sound will arrive to both my ears, having theoretically exactly in the middle. It will have the 2 signals reaching my ears, they will have the same amplitude. So the point is that suppose we have a couple of signals. suppose that the amplitude of these two signals is 1 for this one and 0 for this one. 1 means that it will reach here, my here, and I will locate on this side, and the opposite will happen in the opposite case. While if I have the same amplitude here, I will receive two same amplitude signals, and I will locate the source there. No? So it's pretty easy. You think about doing something like, you see that you're computing with your brain, you're computing these two signals coming from the ears in one single representation, and depending on this, the amplitude, the relative amplitude of the two signals, you can locate the sound source, even if, of course, you close your eyes. So can we reproduce this in some way? Well, there are many techniques for sound spatialization, much more complex than what I'm telling you, but a very easy first demonstration is to consider that the position of my sound source can be of my virtual sound source can be computed in this way. So let's suppose I have something like pause here, and pause can be 0. Pause can be 0 if it's exactly in the middle. So the idea is that I will work on a stereo setup, so I need two outs, and on out and out plus 1, so I can offset my setup, even if in our case, if we're creating two signals for the two channels of a stereo setup, it's useless to control this. This should be 0 and this should be 1, but let's leave our out with a default values here. So the point is that we have to multiply mix depending on the position. So let's assume that we have like var left, then we will have var right, and we have mix, and the point is that we have to multiply these so that we do let's consider our case. If 0 is in the middle, so left could be -1 and right could be +1. Now let's suppose the amplitude here is the maximum one. We have to multiply it times a certain position that we have to scale, and this should be something like this, minus left. Why? Well, let's suppose this is globally we have mix multiplied minus what? Minus pause. That's the relation. So if this is pause and this is 1, then this is not right. I'm making a real-time reasoning with you. If this is pause and it is right, and it is 1, everything on mix should be on our left, and what should we have on the other side? 0. So it's 1 minus pause. 1 minus 1, that's right. And what happens if this is -1? This doesn't work in this way, so we have to think better about this relation, because we will have to scale this down. So like well, we can do this in this way. Well, rather than tricking with mathematics, we say that we go from -1 to to 1 and mix, it's not mix, it's mix pos. Lean position must go from -1 to up to 1, and in case of left, -1 is 1 and otherwise is 0. Then we can do this. Well, this should be right. So let's check. If position is 0, it will be half in the middle. So going from 1 to 0, well, we can make some test. If our position is 0, then we have 0.5. That's right, we have half of the amplitude dedicated to left. So 1 minus 0.5 is 0.5. Let's suppose we are in position -1. We should have all on left. That will be -1, 1 minus 1. Let's check if this works. But this is what is not working, because here we are summing position. We're summing position, so we first calculate position. Right. So we will have 2, which is wrong. The point is that the easy way, there are many possibilities to do this kind of operation, of course. Here we invert the position. So at this point, we have the same applying domain and opposite position. So what happens in this case if we have all on the left? This will be the position on the right, which is 0. And if we are with all on the right, it is 1. And here we are in the middle, which is okay. Okay, this should work. So let's see, left, right. Okay. Oops. Yeah, but this was easy. So let's give 3 dB. Now we need to not this. We need to take a look at the channel. Fine. Now let's do something like x set pause 1, and we got it only on right. Fine. Let's close this. And now let's do 1 neg -1 only on left, which should be fine. Let's do 0.4, 0.8, 0.8, not negative. Okay, so we are creating a sort of linear panning, which is not the best solution, but it's a way to do this kind of thing. So actually, as an example, we can of course add a third slider, not slayer, is a different thing. Third slider, same dimension, place it here, so we have 300. It's better if we do this in this way. And let's close this. So now we have additive synth. And let's see. No, but we're not adding. So now we have still to add the action. The action is easy because SL3 action should set pause me value 0.1 between -1 and 1. So let's see our scope. Let's move it here. We move our windows. This should control the position. Okay, this works. And now we can add, rather than using out is no more useful. We can add a pos. Something wrong here. Pos. That should be something like. Should be something like e modulo 10, so from 0 to 9, and we use this len 0 9 minus 1 1. Let's create our saint, which is created here. Let's add some amp 3 dB amp. I'm doing a cycle so we can. Of course, we can do this quite much slower. Maybe you won't appreciate more. Well, of course, we can do something more extreme. Okay, so well, of course, once you have an instrument, you can create all the things you want with this instrument. What kind of processes, such the ones we discussed in the previous videos. Now, so this is a way of making panning, but this is not the standard way. Well, actually, this is a possibility. You have a function calculating amplitude of signals and then delivering signals directly to outs. That's not the favorite possibility, because there are various techniques and algorithms to place automatically, given a certain position, to create automatically the signals to be delivered on a certain set of channels, typically mapped onto speakers. So suppose you have 8 speakers, you can decide the virtual position of a certain source by creating 8 signals to be opportunely delivered to this multi-channel speaker. And there are various techniques like ambisonics or VBAP or wave field synthesis, whatever. Also, in terms of just placing a position on a stereo setup, this kind of so-called panning, as you have seen here, which is the linear panning, is not very good in terms of results, because typically it creates a sort of hole in the middle effect. So there are other techniques to calculate rather than linearly with other kind of function. How can I say, the weights, the relative weights of the two signals to be delivered to the two channels and then map it onto loudspeakers, of course. So typical way is the following one, but that was interesting for our discussion. Rather than we will use multi-channel expansion at this point, rather than using what we have written down, we will use a specific Eugen. This Eugen is pan2, and pan2 take signals to be placed on a stereo setup. This, in our case, it's our mix. Then what? Then simply a position. It's a how can I say, power-based placement. A position between -1 and +1. That's why I was using -1 and +1, so we can use our pos. And the level, which is a scale, but well, actually we have already scaled before by multiplying by amp times amp, so we do not need the scale. Now, what is going on here is that the output of this Eugen is not a single signal, but it is an array of signals. So actually, what happens is that we are feeding pan2 with a mono signal. We're specifying a position, and by following a certain algorithm, which is a power-based panning, pan2 will create two signals, opportunely scaled, substantially following the same logic as we did before, let's say by hand, with better results. And they will be packed into an array. So we have an array of signals. What to do with an array of signals? Well, it's pretty easy, because if we call this so pan is an array of two signals, we pass pan to our out. Now let's consider that this is a number like 0, and this will be an array like sig1, to just understand, sig1, sig2. So we will have multi-channel expansion, because sig1 produced by pan will be placed on 0, and as there is another element of this array, this signal will be placed on out +1. So we'll have stereo placement automatically. This also happens for other variation on pan that are used for can be used for multi-channel, direct multi-channel expansion, like pan AZ. This substantially, by the way, should work exactly as before. So this is interesting, because it's a sort of the idea that our SynDef has a sort of public interface. We're changing the internals, but the interface is the same. So we have always, also in this case, we have pos and out. That's fine. Let's see if I am right or maybe not. Okay. So maybe we need to see something. This is our stethoscope. We need, let's place this, where am I? X set pos in the middle. Far left, far right. Opposite. Not negative. Fine. So this means that our routine is working correctly. Well, you see that it's perceptually more linear than the example before, because this is power-based panning and works better in terms of distribution than linear panning. So actually we're using this to do multi-channel expansion. So we were, interesting enough, we were using multi-channel expansion to create an array of related signals. Then we mixed all these signals down with mix, and then we re-expand this for stereo placement by using pan. So this is the basic of additive synthesis. There are many considerations that we can add. As an example, the fact that they are perfectly harmonically related, all these components in our spectrum. Maybe it's not always what happens in reality. Sometimes there are out of tune elements, and we can control this, the tuning. All consideration you can find from acoustic of instruments can be applied to our instrument. Of course, we can modify this so that it becomes an event generator rather than an instrument. Well, this can be easy to do. Let's consider this. Var env, it's env gen kr, and we're using some default so it's easier. Perk don action 2. So note that here again we have level scale, so we can scale volume in various places. We have scaled this here directly, but we could have scaled by using level here, or we could scale by using an envelope here. That's the same thing. Now actually our env should be applied after mixing. So env gen times mix. So we have a percussive event, and then we use env. Am I right? I think so. Here. So now this does not apply anymore because we're just creating. So we need to this is not useful anymore. Let's give some. So we're creating events right now. So we can modify our routine. Same stuff, but this time we create directly a saint, and all these will be parameters of our saint, and we will probably have some. Let's wait for a fifth of a second. Let's see. Now, interestingly enough, here we are spawning various events, and they have overlapping duration. So it's really like having various objects. Each of these event takes these parameters that are related to these various relationships we have detailed here. So we already covered that. We can change this maybe. And again, this could be something like well, like choosing, or maybe simply 3. So you have some 3, 6, maybe 2. We're working also on the amplitude. Do we want to say? Okay, so can we use the same approach to introduce other techniques? Well, there are many available techniques. A possibility is to discuss a variation in some sense of additive synthesis, and well, it's not a variation, but conceptually can be thought as a related approach. And this related approach is subtractive synthesis.